This is Classical Physics 2, Physics 220, and we're doing Chapter 17 problems. Now I'm going to do even problems because the syllabus says you guys are doing the odd problems. So we'll do some of them just to see how we do here. All right, so the first problem we're going to look at is problem number 2. And needless to say, I've lost my place in the book already, so I don't know what problem number 2 is. All right, so problem number 2, how many atoms in a copper penny? So the mass of our copper penny is given as 0.0034 kilograms, and it doesn't tell us that. It tells us how many grams there are, but clearly we want to know the answer in kilograms. We also notice that this is in section 17.1 of the book, so 17.1 of the book should add something to the problem. All right, so the number of atoms is going to be the mass of the atom divided by the atomic mass units of copper, because this is copper, times the number of kilograms per atomic mass unit. Okay, so that's our plan. So the number of atoms, our mass, 3.4 times 10 to the minus third kilograms. We look in the back cover of the book and we see that copper weighs 63.546, so we'll round it off to 63.5 atomic mass units. Now the books just use a mu there. I'll say AMU just for the heck of it. And then on page 455 of the book, it says one atomic mass unit is 1.66 times 10 to the minus 27th kilograms per atomic mass unit. Now, it would seem, this is going to be atomic mass unit per atom. Okay, so it's atomic mass units per atom. Now, when we put that in our calculator, we see that, first of all, we see that kilograms go away and atomic mass units go away. And the only thing we have left over is atoms. So I put that on my calculator. And I note that I only have 2 significant digits in my problem, so I'm only going to keep 2 significant digits in my answer, and I'm going to go with 3.2 times 10 to the 22 atoms in 3.4 grams of copper. Okay, so that would be problem number 1. Next problem we're going to do is number 6. So problem number 6, in an alcohol in glass thermometer, the alcohol column has a length of 11.24, 11.82. Okay, so I got alcohol and water. Okay, so I'm going to go and look on page 4, 5, 8. 4, 5, 8. All right, so I've got a tube, and on one side I have alcohol, and the other side I have water. And I've got some length of the alcohol at 0 degrees. So the length of the alcohol at 0 degrees is going to be 11.82 centimeters. And then the length of the alcohol at 100 degrees is going to be 21.85 centimeters at 100 degrees. So now the issue is both in centigrade. What is the temperature if the column length is 18.72 centimeters? And what is it going to be if it's 14.60 centimeters? Okay, so those are the issue. I'm not sure that my picture's right, but I know that my proportions have to be right. So I look at, if I look at the change in temperature, change in length, and I see that I'm going to change temperature by 100 degrees, and my length is going to be changed by 11.03 centimeters. And I see that that's 9.067 degrees centigrade per centimeter. Okay, well, now that I know how much I'm going to change per centimeter, I can then find I'm looking for what temperature do I have 18.75. Okay, so T1, the thing I'm looking for, minus 0 is going to be equal to 18.70 centimeters minus 11.82 centimeters. So it's a proportional thing, and I put that in my calculator, and I find out that well, actually, I have to go and say that that's equal to 9.067 degrees per centimeter before I can do anything. Now I put what's on the bottom on the other side of my calculator, and I find that my temperature 1 is going to be 62.4 degrees centigrade. And then I look at my B problem, and I look at temperature 2 minus 0 degrees centigrade, and I'm going to be at 14.60 centimeters minus the 11.82 centimeters, and I'm going to set that equal to the same 9.67 degrees centigrade per centimeters. And then I'm going to calculate T2, and my calculator says that T2 is 25.2 degrees centigrade. And then I'm going to ask myself, how many significant digits do I have? And it looks like I can probably be okay. Looks like they want me to do it to 4 significant digits, and I only did it with 3, so I should probably go back and rework the problem to 4 significant digits, but I'm not going to. Okay, next we're going to move on and do problem number 10. And I see that problem number 10 is from somewhere. Okay, problem number 10 is from section 17.4, so I'll keep that in mind when I look for the equations. And number 10, to what temperature would you have to heat a brass rod if it's going to be 1% longer? Okay, so I want to be 1% longer. if I start at 25 degrees. So I start at 25 degrees centigrade. How far do I have to heat it up if I'm going to get to 1% bigger? All right, and I find that I have an equation 17-1a that says the change in length is going to be alpha length naught delta t. And I'm sure that if I turn the page, yes I do, page 460, I look and I see I have brass. So I find the alpha for brass is going to be 19 times 10 to the minus 6 per degree centigrade. All right. Now I want a 1% longer. Okay, so I'm going to have 1.01 of L naught is going to equal 19 times 10 to the minus 6 per degree centigrade times L naught times my delta T, and my delta T is going to be some T final minus 25. Okay, I see that L naught goes away, and because I have it on both sides of the equation in a term, and now I've got 1.01 divided by 19 times 10 to the minus 6 per degree centigrade is equal to temperature final, and then I can go, well, plus 25 degrees on the other side. Okay, so I do that calculation and I see that my final temperature, in order for that to happen, 551.3 degrees centigrade is what my calculator is telling me. And then I look at problem 10 and I see that I only have 2 significant digits. So for my final answer, I'm going to pick a temperature of 550 degrees centigrade because I only have 2 significant digits. Okay, we're going to look at problem number 20 next. Okay, problem number 20. Show that the change in density rho of a substance when the temperature changes delta T is given by delta rho is equal to minus beta rho delta T. What is the fractional change in the density of lead sphere when the temperature changes from 25 degrees centigrade to minus 55 degrees centigrade? Okay, well, that's what we're going to do. And so the change in rho, the density, is going to be the final density, rho F, minus the density that I started with, which is going to be mass over volume, because that's what, and that would be mass over volume minus mass doesn't change, over volume naught, and we could call this volume final if we wanted to. Okay, and we could rewrite that as mass over volume naught plus the change in volume minus mass over volume naught. We could do that if we wanted to, and we do. And then we could rewrite it as mass over volume naught times 1 over 1 plus beta delta t minus 1. So we could do that. And then we'd want to go in and come up with a common denominator. So mass over volume naught, 1 over 1 plus beta delta t minus 1 plus beta delta t divided by 1 plus beta delta t. And then we could call that, well, mass over volume naught is just rho. So that'd be rho times minus beta delta t divided by 1 plus beta delta t. And now we're going to do one of those physical things. Now, I have beta delta t on both the top and the bottom. Okay, but I'm going to say that, you know, beta delta t is pretty close to 0, which implies 1 plus beta delta t is equal to 1, or thereabouts. It's about equal to 1. And then I'm going to say that this is going to be rho times minus beta delta t. All right. Well, only a physicist would do something like that. So for my final answer to part A is going to be the change in rho is going to be minus rho beta delta t. All right, so that's going to be my answer to part A. And now I'm going to start looking at part B. So I'm going to take what I started with, change in rho is equal to minus rho beta delta t, and I'm going to divide top and bottom by rho. All right, so I have delta rho over rho is equal to minus beta delta t. And then I'm going to get that this is lead. So I'm going to go look up what beta is for lead. And there it is. I see it 87 times 10 to the minus 7. Okay, so 87 times 10 to the minus 6, my mistake, degrees centigrade. My change in temperature, I'm going to go final temperature minus 55. Initial temperature 25, and I'm going to put it in my calculator, and I'm going to get 6.96 times 10 to the minus third, and then I'm going to ask, what did the problem ask me to do anyway? It said, problem number 20, what is the fractional change in the density? All right, so that would be fine. That would be the fractional change in the density. Or if I wanted to, I could call it 0.7%. I could do that too. And now the issue is, how many significant digits do you think we have in problem 20? And maybe there's 2. So if there's 2 significant digits, I'd have to round it out. That would be my final answer. And problem number 24. And problem number 24, and we're still in the same place. I've got 28.4 kilograms of aluminum. And it's in a cylinder wheel of radius 0.41 meters. And it is rotating about its axis on a frictionless bearing. Angular velocity, that's an omega in case anybody is worried about it, 32.8 radians per second. If its temperature is raised from 20 degrees Celsius up to 95 degrees Celsius, what is the fractional change in omega? Okay, well that seems like a reasonable thing to figure out. So the first thing we need to know is what the moment of inertia is for such a thing. So we'd have to go back in our book, and I forget exactly what page it's on, but there's a table of angular momentum things. It's probably in chapter 10. There we go. On page 260 in your book, you can see that a cylindrical cylinder, the angular momentum is going to be 1/2 the mass times the radius squared. All right, so we're going to have to come up with that. And we're going to know that the angular momentum, the initial angular momentum that we have, is going to equal the final angular momentum. So we note that that's the case. And we also know that the angular momentum naught is going to be I naught omega naught. Okay, so we know that that's the case. And we know that that's going to have to equal the final angular momentum, whatever it is, final inertial, well, anyway, what's it called? Moment of inertia. The final moment of inertia times omega final. Okay, so those are things that we know, and from that we can calculate omega final. Okay, so that's what we're going to do before we run any numbers, and we find that omega final is going to be the initial inertia divided by the final moment of inertia. We find that that's going to be 1/2 m r naught squared omega squared divided by 1/2 m r, the new r, which we haven't calculated, squared. We see that the masses go away, the 1/2s go away, and we have r naught squared omega squared divided by the final radius squared. Okay, and then we say, well, what is going to be, we're looking for the fractional change, so we're going to look at the change in angular velocity divided by the angular velocity. Okay, we're going to say that that's omega final minus omega naught divided by omega naught. And we know, we already found out the omega final, so we'll put that in. R naught squared omega naught divided by R squared minus omega naught divided by omega naught. Okay, so we end up having the omega naughts all go away, and we have R squared naught divided by R squared minus 1. And then we'll say, well, gee, that's R naught squared divided by R naught plus the change in R squared minus 1. Minus 1. And then the change in R, the change in R, we know that to be something. So we got R naught squared divided by R naught plus the change in R is going to be alpha R naught delta t. And that quantity is going to be squared, and we're going to subtract 1. Okay. Then we're going to do something only a physicist would do, probably. And now normally what we would say is that if I was a mathematician, I'd say a plus b squared is equal to a squared plus 2ab plus b squared, right? That's what we normally do, and that's what we have down here. But because we're physicists, we're gonna say that the middle term 2ab isn't all that significant, and we can just ignore it in doing our calculation. And we can call this 1 over 1 plus alpha delta t quantity squared minus 1. So we could do that. All right. And then we could go and find a common denominator. Okay, so our common denominator is 1 plus alpha, doesn't look like an alpha, 1 plus alpha delta t squared 1 minus 1 plus alpha delta t squared. So we could do that, and then we could go and say, well, 1 minus 1 plus 2 alpha delta t, and because we're physicists, we don't necessarily have to do the same thing every time, right? So this time I'm going to do the expansion and keep the center term, divided by 1 plus alpha delta t squared. Okay, then I've got a 1 and a minus 1. Now remember that this is change in omega naught. So this is the fractional change that we're looking for. Okay, so now we've got minus 2 alpha delta t minus alpha delta t, the quantity squared, divided by 1 plus alpha delta t, the quantity squared. And we could say, well, you know, this alpha delta t guy, He's pretty much 1. He's pretty close to 1. And if we do that, yeah, we're going to end up with pretty close to 1. Yeah, it's pretty close to 1. We're going to end up with delta, the change in omega naught as being minus 2 alpha delta t. All right, now we throw in our alpha, we throw in our delta t, and we end up with minus 2, 25 times 10 to the minus 6, because this rod is made out of what? And I forgot already. And not only that, not only did I forget already, but I'm on the wrong chapter altogether, so that's pretty bad. Here's problem 24. Aluminum. Alright, so, yep, there it is. 19 times 10 to the minus 6. 25 times 10 to the minus 6? How did I get that? Nope, 25 times 10 to the minus 6. Okay, and my delta T was 75 degrees. Yes, it is 75 degrees. And so my fractional change minus 3.8 times 10 to the minus 3. And that would be my fractional change in omega naught. Now we only made 2 or 3 assumptions in there going through the problem to come up with that answer. But that's the nature of the game, so we get to do that. And now we're going to look at problem number 30. Problem number 30. Typical temperatures in the interior of the Earth and the Sun. So temperature interior of the Earth, 4,000 degrees. And interior temperature of the Sun, 15 times 10 to the 6th. 15 times 10 to the 6th. Now what temperature do I need in order to have fusion to occur? Anybody know? Obviously it's greater than 15 times 10 to the 6th, or some number less than that. It's about 1,000,000 degrees, and that's 1.5 million, so that's about right. What are those temperatures in Kelvin? Oh, well, okay. So we're going to add 273 to each of them. So the temperature of the Earth, 4273 degrees Kelvin, and the temperature of the interior of the Sun, 15, 1,000,000, blah, blah, 273 degrees Kelvin. Well, obviously we don't have that many significant digits for the Sun. So that begs another question. So here's the Sun. There's the interior of the Sun. Now it turns out that only the middle 1/3 of the Sun is hot enough to have fusion. So my fusion that's happening is happening in the core of the Sun, the middle third. So I've got a gamma particle that's made in that fusion. The issue is, how long will it take that gamma particle to travel to the surface of the Sun before it travels the Earth? And it gets the Earth in about 8 minutes or so. But how long will it take for it to get from where it was made in the center of the sun to the outside of the sun. And so we'll think about that for a little while, and then we'll write down the answer. It's about 500,000 years. So 4,900 years ago, 4,090 years ago, 490,000 years ago, the center of the sun could have quit fusioning and we wouldn't know about it yet because the energy hasn't come out that far. It's so hot. Okay, well, anyway, that's beside the point. This is the A part of the question. Now we got to worry about the B part of the question. So the B part of the question is, what is the percent error? So we want percent error by calling degrees centigrade Kelvin directly. Okay, so for the Earth, it would be an error of 273 out of 4273 times 100%. So it's around 6.3% error. For the Sun, it would be 273 divided by 1,500,000, 273, and that would be about 1.8 times 10 to the minus 3%, which is not very much of an error. Not very much at all. Okay. So we're going to look at problem number 34. Number 34. And 34. Now we're dealing with ideal gases, and which means we're dealing with things that have to do with PV is equal to nRT. So we know that that's what we're going to have to deal with. And number 34, assume that I have 14.00 moles of helium. Okay, and the gas is at, my temperature is at 10 degrees centigrade, and my pressure is at 0.35 atmospheres, and this is a 0.0 sitting there. So I have 3 significant digits in all my answers, and I want to find the volume of the gas, and then I want to find the temperature of the gas if it's compressed to precisely half the volume, and it's going to be at a different temperature. Okay, so we'll worry about that later. Okay, so we'll worry about the A part of the problem first, and we'll take our PV is equal to nRT equation and change it to the volume is equal to nRT divided by P. And first thing we'll note is that if I'm not in Kelvin, I'm going to get the wrong answer. So this is 283 degrees Kelvin I have to put into the problem. All right, so my volume is going to be the number of moles, 14.00 moles. And then the R I want to use is one that has moles in it, so that would be a convenient thing to have. 8.314 joules per mole Kelvin times my temperature, 283 Kelvin, divided by my pressure, 0.35. What's my pressure? What problem am I on? Okay. Times my pressure, 0.350 atmospheres. But I'm going to have to be in pascals, so I'm going to have to change that to 1.013 times 10 to the 5th pascals per atmosphere. Okay, so that's the calculation I'm going to have to do, and I'll take out my calculator and see what I get, and I won't bother you with what keys I'm punching. Hopefully I'm punching the right ones. And it looks like I've got 0.929. 0.929 meters cubed, because my volume is going to be in meters cubed under those conditions. All right, now for the B part of the problem, I want to know, I'm going to change the atmospheres and I'm going to change the volume. So volume is going to go to 1/2 my initial volume, so that's 1/2 of 0.929. Okay, so I got that in my calculator. Divide by 2 is 0.464 meters cubed. We'll put a 0 in front of it. Protect the innocent, and my pressure is going to go to 1 atmosphere. Okay, so now I'm going to use P1V1 over T1 is P2V2 over T2, because the number of moles didn't change. And I'm going to end up with temperature 2. So I do some cross multiplication. P2V2 T1 divided by P1V1. And what am I doing? Uh-oh. Uh-oh. We got a problem. We got to move back to the first A question. And the problem is that this is a gauge pressure. And we can't use gauge pressure. We need pressure absolute. Oh, bummer. So that means that this is really 1.350 atmospheres. All right, and then we come back here, and this is 1.350. And my volume when I get done is 0.2410 meters cubed. And half of it is going to be 0.1205 meters cubed. Okay, and my pressure is not 1 atmosphere, because again it's 1 atmosphere gauge, a gauge pressure of 1 atmosphere, so it's 2 atmospheres absolute. All right, so now I'm back. All right, so I got 2 atmospheres, and that's what I get for not reading the problem. 0.1205 meters cubed divided by 1.350 atmospheres, and volume 1, which is 0.241 meters cubed. And what was temperature 1? 283, right? 283 degrees centigrade. I ran out of room there. That's not good. Bad form. So T2 is going to be 210 degrees Kelvin. Okay, so I didn't double that, but I increased the atmosphere and I took the volume by 2. Why did the temperature go down? Alright, that's half as much. Actually, yeah, it's going to go down a little bit. Okay, that looks good. Okay, so that's what's going to happen to me on problem number 34 if I bothered to pay enough attention so that I can not mess it up too bad. Number 44. Okay, so I got number 44. I have a helium-filled balloon. Here we're doing problem number 44. A helium-filled balloon. So I know it's helium. Escapes from a child's hands at sea pressure, sea level. Sea level implies 1 atmosphere. And at 20 degrees centigrade. And I'm going to go to up to 3,600 meters, which isn't that far up, and at 5 degrees centigrade. And the pressure where the pressure is 0.68 atmospheres. Okay, so I know that. And so I want, how will its volume compare to that at sea level? Okay, so that's the issue. So we're going to use P1 V1 divided by T1 is equal to P2 V2 divided by T2. And the first thing we'll recognize is that I have to have my temperatures in Kelvin. So that's 293 degrees Kelvin, and this is 278 degrees Kelvin. Okay, so I have to know that. And I'm comparing, so I'm going to just go V2 is the V1. Okay, so I'm going to put V1 on the bottom, so I'm going to have P2 T2 divided by P2 T1. Okay. So pressure 1 atmosphere, temperature 293 Kelvin, divided by 0.68 atmospheres, and temperature 278 Kelvin. And when I get done, I get a 1.4 out of that. So I'm going to say that V2 is going to be 1.4 V1. So that's how they compare. All right. Now we're going to look at something was wrong with that problem. That was way too easy. Number 50. I'm going to have to find more difficult problems than that, I guess. An air bubble at the bottom of a lake, 37 meters deep. All right, so so I need a lake. So there's the top of the lake. This is my lake. It's filled with water. Okay, and I got this air bubble down here. Okay, and I'm 37.0 meters down. Okay, so the volume when I'm at the bottom of the lake, we'll call it volume 1, is 1 centimeter cubed, which probably isn't anything that I really want. If the temperature at the bottom of the lake, so temperature at the bottom of the lake is 5.5, then I'm going to want that in Kelvin, and I'm going to call the 5.5, I'm going to add 33 to whatever. I'm going to run out of room when I do it. So we're going to call T1, we're going to call 273.15 plus 5.5 is going to give us 378.65 K. Now, we really don't need that many significant digits, but we'll go with it anyway. And at the top, so temperature on the top, we'll change color here. Temperature 2, which is going to be the top, 18.5 degrees centigrade plus 273.15. And you guys have told me to change this over here, right? You want that to be a 2. Okay, that's better. All right, now I'm going to add those guys up, and 0.65, 1, 1 to carry, 1 to carry, 9, 2 Kelvin. Okay, what is the volume of the bubble just before it reaches the surface? All right, volume just before it reaches the surface. All right, so now, is it salt water or is it fresh water? Because it will make a difference. And it won't make very much of a difference. The problem doesn't say, so that means we're free to call it fresh water. Well, it's a lake, so it's going to be a fresh water. So the pressure on the surface times the volume on the surface is going to equal, or divided by the temperature on the surface, has to equal the pressure submerged, temperature, volume submerged, divided by the temperature submerged. All right, now, do we know all these things? Pressure on the surface, yeah, we know that. But we don't know the volume on the surface. Okay, so I'm going to solve for volume on the surface. So volume on the surface, that was good. Volume on the surface is going to equal pressure submerged, volume submerged, temperature submerged, times temperature on the surface divided by pressure on the surface. Okay. The only thing we really don't know is the pressure submerged, so we'll have to get that. Okay, so volume submerged. Now, we know that on the surface, the pressure is 1.013 times 10 to the 5th pascals. So the pressure submerged has to be that pressure, PA, plus the pressure of the water. And so I've got 1 times 10 to the 3rd kilograms per meter cubed times 9.8 meters per second squared times 37.0 meters. So that's going to be the pressure submerged. And I just ran out of room. Okay, so I'm going to have to multiply that times volume submerged, 1 centimeter cubed, and I have to multiply it times the temperature surfaced. Temperature surfaced. Where's the temperature surface anyway? There it is. 291.65. 291.65 K. So that guy there is sitting at the end here where I can't put him. Okay, and then we're going to divide it by the temperature submerged. Where's temperature submerged? 27865. 278.65 times the pressure on the surface, which is 1.1013 times 10 to the fifth pascals. Okay, and we'll go back. Okay, you're complaining that should be a little a. I agree, that should be a little a there. Little a. Alright, so we're going to multiply and divide, and we're going to get the volume on the surface just before it breaks the surface, and my calculator says 4.79 centimeters cubed. Now it looks more like a squiggly line than centimeters. Centimeters. There, is that better? Cubed. And that would be the volume on the surface. Alright, well that wasn't all that difficult. We had to figure out how we're going to get that volume of water though to get to a pressure. And had to remember that from chapter 10 or 11, someplace around there. Alright. Number 50. Well, that's the whole purpose of doing Physics 1 before Physics 2. All right, number 54 is next. Estimate the total number of moles and molecules of water in the surface of the oceans. So A, we want moles, and B, we want molecules. Of water, so we want H2O, we don't care about the salt or anything else, in the oceans. Okay, so we're going to assume 75% of the Earth is covered with oceans, and it's covered to an average depth of 3 kilometers. Okay, well, if we look in the front of the book, we'll find out that the radius of the Earth is something. So the mean radius is either 6.38 radius Earth, 6.38 times 10 to the 6th meters. Okay, is that good? Look at it again to make sure I got it right. Yes. 10 to the 6th meters. Okay, so I got that from my front cover. So now I'm going to want to know the volume of the H2O is what I'm on. Volume of the water. Okay, so volume of the water. Okay, it's going to be 0.75 because it's only 75% times 4 pi r squared of the Earth. Times the change in the radius. Yeah, change in the radius. So that's at 3 there. All right, so that looks good. So, and where do I get the 4 pi r squared? And it's 4 pi r cubed, right? 4 pi r cubed. The volume. No, we just want the surface area. 4 pi r squared, right? Yeah. So that's why we're doing the change in, we'll call it change in height. So all we're doing is looking at the surface area of the Earth, 4 pi r squared, and going with 0.75, and then multiplying it by the height of the surface area to get the volume. Okay, so we put all those numbers in our calculator, and we get 1.15 times 10 to the 18th meters cubed of volume. So now at this point, all we have is dimensional analysis is all we're going to have. So we look at the A answer, and we want the number of moles. So I've got 1.15 times 10 to the 18th meters cubed, and I'm going to multiply that by 1025 kilograms per meters cubed of water. Now, why am I multiplying it by 1025 for anyway? I thought we were dealing with fresh water. No, it's the ocean, so now we got to do it with salt water. Okay, so that's how we're doing it with salt water. Times the radius of the where was I? Okay, so I got 1 mole per. I've got H2O. Okay, so that's H2O. So this guy here has atomic mass is 16. This guy here is 1, but there's 2 of them, so that'd be 18 times 10 to the minus third kilograms per mole. Okay, so that looks good. So now I got moles go away. No, 1 mole per that. So this isn't per mole. I already put the mole on top. All right, so 1 mole per that many kilograms. All right, that's fine. Kilograms goes away, meters squared goes away, and all we have, meters cubed go away, and all we have is moles left over. All right, so we put that in our calculator, and we end up with 6.55 times 10 to the 22nd moles of H2O. And then we ask ourselves the B question, which is how many atoms do I have? Well, if I have 6.55 times 10 to the 22 moles, how many molecules, not atoms, times Avogadro's number, 6.02 times 10 to the 23rd molecules per mole. And so I end up with somewhere around 4 times 10 to the 46 molecules. Okay, so that ends the problems for chapter, whatever chapter this is. Anybody know what chapter this is? This is 17.